Yes.
Yes? How'd it go? I didn't look.
Some of that stuff was.
It was pretty good. There were a couple of them that I was like,
Some of them were like energy vaporization or enthalpy of fusion.
Okay.
I don't recall.
I don't think we.
I mean, that's just the heat of,
I
like,
remember doing it like last year, so I just kind of guessed.
And there was also one that was like, what would produce the least amount of error?
yeah,
Okay.
that one was hard.
That was
Okay.
mine.
all right. Okay. Cool.
Could have been a lot worse. Though.
Okay, so we are moving to chapter 7, which it seems crazy that we are that far. Some of this is going to be review, some of it's going to be new. So, do you remember Rutherford last year with the gold foil?
Yeah.
Yes?
He sent a bunch of
They didn't
So he shot the alpha particles into it, right? And he expected them to go where?
Didn't that irradiate itself? That was pretty fun.
Yeah, he did. He did irradiate himself doing that. He expected those alpha particles to go where when he shot? Straight through. But what happened to them? Some bounced back, some bounced off. And what did he discover? The nucleus, right? Because the alpha particles had a positive charge, the nucleus had a positive charge, they ran into it and they bounced off. So this was all based on the attraction between positive protons and electrons. This next thing, I have star, 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 is huge. All right? So this is going to be like one of the 3 buzzwords in AP Chem on the AP test. You'll probably eventually write down for something. So this whole thing is governed by Coulomb's law. But now this pen is not.
I'm gonna borrow one of my pins.
No, I'm gonna try.
You want a pink pen?
No, I don't know where my blue pen went. Like, oh wait, I know. It's in my backpack. We're good. I think. Why is this in my backpack?
What is that?
It's like an airplane thing you put together. I have found my blue pen.
Hey.
I have found my blue pen. C-O-U-L. That's going to look weird. Coulomb's law.
Is it you on your list?
C-O-U-L-O. Coulomb. Wait, how do you spell Coulomb? I want to spell this right.
No, I did this in pen.
You can change an O to U. C-O-U-L. C-O-U-L-O. I spelled it right.
Oh.
We're good. Whew. Whew. All right, so I feel better. It says the force between 2 charged particles. So let's say that is Q1, Q2, comma, is inversely proportional to the square. Does this sound like an equation? Yes, it is. Of distances between them. So once again, the force between 2 charged particles, Q1, Q2, is inversely proportional to the square of distances between them. So there's a couple different equations that you may see for this. You may see this. Force equals K times Q1 times Q2 over D squared. And the K is just a constant. It's going to be some weird constant with weird units that's going to cancel stuff out. But a lot of the times you don't see it with the K. So many times you see it force just equals Q1 times Q2 divided by diameter or distance squared, not diameter, distance squared. What's the point of this? Well, here's the point of it. So if charge goes up, what happens to the force? Force goes up. The force goes up.
Is that D squared?
D squared, yes. If the distance increases, what happens to your force? It goes down how? If the distance increases, the force I should say the force, goes down squared, right? Yes? So increasing the distance really decreases the force.
Wait, why does the second equation not have a K?
Because a lot of times I just leave the K out because it's just a constant. So you'll see either version of this, but a lot of times you just leave the K out because it's a constant. So if Q1 and Q2 are the same, they will repel, right? Because like charges repel. Agreed? You guys okay with that? If Q1 and Q2 are opposites, they will attract because opposites attract. So, what would this look like if you had to do math with this? It's easy. So here we go, a pair of particles where charge on each particle is tripled, and the distance triples. How does force change? So my force is going to equal 3 times 3, because I'm multiplying both of my Q's by 3, divided by what?
It says the distance equals 9.
Divided by 3 squared, right? Because my distance was 3. The distance went up by a factor of 3. So you're kind of putting in what factor is it changing by?
The original charge was just like 1.
Yes, we're assuming the original charge was 1. So this is kind of like, by what factor is it changing? 3 times 3 is 9. Divided by 9 is 1. So did it change? None. No change. Try the next two.
Okay, so how do we know if it changed?
It'll be different.
From what?
Let's do the next one. If the charge on one particle is times 2, so F equals, the first one's 2. The second one is times 3, but the distance is constant, so my distance is going to stay 1, because 1 squared is 1. This is going to equal my force going up by what? Yeah, force goes up by a factor of 6. Force goes up by a factor of 6. That's how you know, Jawi.
When you say force, is that just what is that force?
So the force between two particles. So it could be a repelling force, Megan, or it could be an attractive force. It just depends what their charges are. If the charge of one particle goes down by 1/2, so I have F equals 1/2, and that means the other one must be doing what? If it doesn't say anything, we're assuming it's going to. Does it say anything about the other particle?
No.
So we assume it is 1, just stays the same. And the distance goes up by 2, 2 squared. That's going to equal 1/2 divided by 4. Agreed? Multiplied by the reciprocal, 1/2 times 1/4 is 1/8. So my force is 1/8 of what it used to be. So that is very basic Coulomb's law. Are we going to be doing something like that on the test? No, not at all. We're going to be comparing molecules, okay? We're going to be comparing different molecules and their charges, okay? So, Bohr model. Bohr said that electrons can only travel in fixed orbital shells. Is that true?
No.
No. They're all over, right? They're going all over the place. So, let's draw sodium, a Bohr model for that. So, a Bohr model for sodium, this is what we learned freshman year. How many go in the first shell? 2. How many go in the second shell? 1, 2, 3, 4, 5, 6, 7, 8. Leaving how many for the third shell? 1. Right? So my third shell is going to have 1. How many valence electrons does sodium have? 1. What would the Lewis dot structure for sodium look like?
Just like 1, 2, 3, 2. And then
1 dot, right? Because Lewis dot structures only show valence electrons. 1 dot. If we used a spectroscope, that's really fun to say. Kind of like a microscope, but spectrum. It was found that gaseous elements emit electromagnetic radiation. Wow, that is not big enough blanks. I need to make that bigger. Magnetic radiation. Do you remember last year in CP Chem when we had the tubes and we were looking through the tubes with the thing? What's up?
Vilma?
Nope.
No. Okay.
She was here first period?
According to the attendance, but I don't know if she got missed.
Okay.
Thank you.
You're welcome. Remember we looked at the tubes with the spectrum gratings?
Oh yeah, it was like all the little tubes. and
Yes.
colors?
Oh, is that like
Yes.
Oh, that atomic emissions.
Yes. That's what we're talking about here. We're going to do that lab again, but like do math with it this year. So we're going to do that lab again, but actually do math with this. So that'll be next week. Can I flip my page? Okay. So, oh, sorry. That copied weird. When heated. Okay? So you have to, let's put that all together. Using a spectroscope that was found gaseous elements emit electromagnetic radiation when heated. Okay? So, the electromagnetic, that should be an arrow. I don't know why I did that. Emitted is emitted in tight light packets. Anybody remember what those energy packets are called? It's a Q word. Quanta. Quanta. Because this is all about the quantum theory. And each element has its own unique pattern of radiation called a spectrum. And that is what you saw in the grading. Remember looking through those little squares? You saw all the lines? Yes. It was later found that electrons absorb. That electron absorbs energy and were promoted up. They were actually promoted up a shell further from the nucleus. So we excited electrons. By putting energy in, we actually excited electrons. When the electron comes back down, right, because it's only excited for a second, then from the excited state, so that's called the excited state, to the ground state. Why did I just, what in the world? I cannot write today. To the ground state. From the excited state to the ground state, it releases that absorbed energy as a line in the spectrum. Since the shells are in fixed positions, the difference in energies between them, the wavelength, symbolized by Greek letter lambda, that's one of my better lambdas I've ever drawn in my life, I would say, of the line of the spectrum from electrons returning to the ground state is fixed. That creates a pattern for each element. So you would see, I don't know why they didn't copy, right? The Roy G. Biv lines through the grading. And maybe you saw like 2 oranges, 1 green, 1 indigo, which indigo doesn't exist anymore. But
Wait, really?
no. Scientists have recently decided the spectrum is now Roy G. Biv. The I in Biv is gone.
That's crazy.
Because they're saying that the human eye did not determine enough between indigo and violet. Yeah. I know. Just like Pluto. Pluto's still a planet to me. No? You just think it's a rock out there floating?
Yeah.
See, you never learned.
A really big asteroid.
Is it-
But like, here's the thing. You guys never learned Pluto as a planet.
Oh.
That I did.
It's like a-
Which is weird. To think like,
It's like
that's
a-
one thing in science that has changed since I was a kid.
Indigo's like a bluish.
Indigo's like a bluish purple.
Yeah. Then violet isn't a bluish purple.
Look. They
Red.
say the human eye can't determine. Look at a rainbow the next time you see one. Tell me what, report back to me.
It's red.
Okay, that's all kind of stuff we talked about last year. When an electron gains enough energy to overcome, so it actually overcomes the attractive force from the nucleus. Now things are getting crazy. It is what? It's ejected. It is actually ejected.
Vanished.
Yes, it's gone. You can actually shoot an electron off of an atom. This depends on the distance of the electron from the nucleus, and this is called ionization energy. Ah, you guys see where I'm going with this.
This was one of the periodic trends we had to study.
Yes, periodic trends coming back. Well, you should. Bohr, comma, Planck, comma, and de Broglie. Doesn't that sound like a law firm from the 1600s?
I feel like there's too many people.
Bohr, Planck, and de Broglie.
Like it was.
Like
if it was
Critchfield,
Planck
Critchfield and
Broglie,
Johnson. You know it does.
If there's 3 people, it sounds kind of.
Also, from their data, said that the electron also acts like a. Electron can act like a particle. What else can it act like? A wave.
Isn't that like light as well?
Yes.
Is that
So,
because it's small, which is supposed to be-
That's the duality of an electron, right? Can act as a particle or a wave. Yes. And waves are defined by wavelength and what else? Frequency. Wavelength and frequency, which is lambda and V. We are not going to be using V for frequency. That's how our book does it. So here we go, wavelength, which is lambda, is determined by 2 repeating points on a sine wave. Draw in the air what a sine wave looks like. Yeah, this is a sine wave, all right? So there's a sine wave. I'm going to draw a line through a sine wave, like so. What is the line it goes through called? Rest. So that is rest. If I labeled from rest to crest or from rest to trough, what are those called? Amplitude. That is amplitude. Distance from a crest to a crest is called a
Oh, that's a wavelength?
wavelength. That is a wavelength. Or it could be from trough to trough, halfway to halfway. It just has to be from the same point to the same point. So amplitude, rest to crest or rest to trough. Wavelength is crest to crest or trough to trough.
Can you leave that up there for a second?
I can leave that up there for a second. Frequency, which we're going to use letter V, like I said, is the number of waves that pass a fixed point per what? What was the unit for frequency? Per what? Do you guys remember a per second? I talked about this last year. So this is measured in, a lot of the time, seconds to the negative first. And last year I told you a per second is a what? What is the unit for frequency? A 1 over a second, an inverse second, a per second. Hertz. It's a hertz, which is symbolized by Hz. Hz for hertz. The speed of light can be calculated considering the frequency and wavelength of radiation. So speed of light, c, is equal to wavelength times frequency. Also, you guys need to know what c is. What is the speed of light? Anybody remember from last year?
Big number.
3.00
Was it 10 to the 8th?
times 10 to the 8th meters per second.
Oh, it's over there.
It's also on the yellow sheets. It is also on the yellow sheets. Also on the yellow sheets. 3.00 times 10 to the 8th meters per second.
All electromagnetic waves, but not.
All electromagnetic waves travel at the speed of light. Radio waves, light waves, X-rays, right? They can have different wavelengths, but they still all travel at the same speed. So what's different between those? Wavelengths and frequency, right? But still moving at the same speed. Still all moving at the same speed. Microwaves travel at the same speed as X-rays. Gamma rays travel at the same speed as FM radio. Flip the page. Here it is.
There we are.
All right. So this is the electromagnetic spectrum. This is the electromagnetic spectrum. Let's draw it short wavelength to, long wavelength to short wavelength, or low frequency to high frequency. That's how we're going to draw it. So long wavelength to short wavelength or low frequency to high frequency. So on this side, we're going to have low energy, we're going to have a long wavelength, and we're going to have low frequency. On this end, we're going to have high energy, we're going to have a short wavelength, and we're going to have a high frequency. So, low energy, long wavelength, low frequency on the left. High energy, short wavelength, high frequency on the right. So, lowest energy on the spectrum is what? You guys got to know these. Anybody remember from years past?
Is it radio?
Radio. Yes. It is radio. Specifically, split in two, what's the lowest type of radio? AM or FM?
It's AM.
AM and then FM. This is why AM radio, it has an even longer wavelength. You can hear AM radio farther away. But AM radio has lower energy, that's why you get that, right? You get more of that background noise because it's not as strong of a signal. Whereas if you're listening to 104.5 WQKT Worcester, you can hear that only till you get to like the windmills in Indiana. Anybody ever driven 30 all the way to Indianapolis? It's horrible. There's just a bunch of windmills out there. There's nothing.
Windmills are cool.
But when I was dating my wife, when she was still in college, she went to Indiana Wesleyan. So I drove 3.5 hours, 3.5 hours all the time one way.
That's crazy.
And then 3.5 hours the way back. I also almost fell asleep many times
What was driving?
on the way home. But I would just unroll my windows and just like have like cold air like slamming me in the face. So I'm glad I didn't, because I probably wouldn't be here today. So Schrodinger and Heisenberg, this should be an arrow. I don't know why that didn't work. They said, oh wait, we never finished this. I'm sorry.
Only radio waves.
Radio waves, then what?
They're the only ones that exist.
Microwaves. Microwaves. Here's going to be my visible light. Well, I'm doing visible light first. Because visible light is Roy G. B. So I took out the I. Took out the I. So what's going to be just below red?
X-ray.
Infrared.
Infrared. Because infra means below.
Bruh.
And then what's going to be just above violet? Ultraviolet. Because ultra means above, UV. So think about what the letters mean, what the words mean.
Is it micro than gamma?
Micro? Not micro.
We already did that. X-rays.
X-rays. X-rays. When you go to the dentist, do they put the thing around your neck when you're getting an X-ray?
Yeah.
They should.
I just get the nice big.
It's like the big
You
vest.
get the
That's
vest.
the best.
There should be a neck part too.
There's not.
Okay.
Why are they called X-rays?
X-rays? I don't know why they're called X-rays. That's probably just what Madame Curie named it. Probably that's why. Which she died. Obviously everyone has died up to this point, but Madame Curie died from the radiation of discovering the X-ray. But she was kind of awesome. Kind of awesome. A woman hero of science, for sure. And then I like to say cosmic for the highest powered. Same as gamma rays, right? Gamma rays are part of that, but there's cosmic radiation hitting the Earth all of the time. Okay, Schrodinger and Heisenberg said you can never find the momentum or position of an what? Electron at the same time. At the same time. Here's how I usually describe this. Close your eyes. I think I did this last year. I don't know if I did this in CP Chem or not, but Brady wasn't in my CP Chem, so we're going to do it again. What? Oh, neither was Megan. Okay, so close your eyes. Pretend like you are in a walk-in cooler. I don't know why I would choose this. It's not cold though, it's just a completely black room. In this black room, there is a helium balloon floating in the middle of that room. And what you have to do is tell me what is the position of that balloon. what would you have to do to find the balloon?
Feel it?
Smoke lamp.
Okay, you guys open your eyes. This is weird now, okay? You'd have to be doing this, right? You have to be feeling until you hit the helium balloon. But here's the problem. Once you hit the helium balloon, what have you done to the balloon?
You moved it?
You moved it. That's Heisenberg's uncertainty principle. Okay? So, he's saying, because electrons are so light, right? As soon as you discover where they are, well, then you've changed the momentum or the location of the electron. Make sense? That's a pretty good description of something that's kind of complicated. Okay. This led to the quantum mechanical model of the atom. You are right on top of it today, Megan. So, I'm going to go back to regular notes at this point. We're going to pause here and go back to regular paper.
Wait, if you had like absolute zero where the atoms didn't move, like did you find the locations?
Well, electron microscopes a lot of times have to be in super cold conditions. So
I'm just trying to think of ways to rate like the Heisenberg.
it would be hard. It would be hard. Because the cold, if you have 0 Kelvin, matter stops moving. So maybe, I don't know, you'd have to Google that. It's very hard to find the location of an electron. Okay, so this is still, if you're keeping track of in your notes, I like to mark what we're doing. This is still chapter 7, which is electrons and atoms. This is all about electrons. And we're talking about 3D structure of electrons. So 3D structure. Megan was just talking about the electron cloud. The electron cloud. So here is my electron cloud. Isn't that a nice cloud? That's exactly what it looks like. An electron cloud is where an electron is most likely. It's where it is most likely to be found. So these electrons are like zooming. If this is like the nucleus, they're zooming this way, this way, this way, right? They're zooming all around so fast that it kind of makes a cloud. Actually isn't one of my worst drawings, in all honesty. We determine energy levels. And those are split into sublevels. And those are split into orbitals.
Oh, yes.
And the orbitals can hold how many electrons? You guys remember from last year? At most, how many? 2 electrons. At most, 2 electrons. And then in the orbital, we also talked about electrons must have opposite spins. Do you remember the one up, one down? Yes? We did that. Promise. I promise. One up, one down. Off-ball diagrams. We talked about off-ball diagrams.
The boxes.
We did. All right? The boxes, right?
Oh, yeah. Oh.
Like this would be like the 1s2, right?
Yeah,
Okay.
oh.
Yes.
Uh-huh.
So this would be electron 1, this would be electron 2. Okay, you guys are with me. There's 4 energy levels that you got to know. One is S. So the S is kind of a spherical shape. Okay, look at this 3D sphere I just drew. P is a dumbbell. So the p orbital looks like this, dumbbell shape. D orbital is super 3D. So it's kind of like 1 there. There's kind of like 1 here. And then there's like 1 coming out of the board at you. Like, so there it is, 3D.
What does it say must have opposite?
Opposite spins.
Oh, spin.
Opposite spins. So there's my d orbital. There's my d orbital. And then F, the shape's kind of weird. All right? Shape's kind of weird. I'm not going to draw that. You're not responsible for knowing that.
It's just a question.
I just put a question mark, okay? You guys can look that up. Now, how do these orbitals fill? Here's how they fill. So, for n equals 1, my quantum level 1, I can only have 1 orbital. So, this is my s orbital. S orbital can hold how many electrons? 2 electrons. N equals 2. Has 3 orbitals. So this is 6 electrons, which is 3p orbitals. This is how I teach this, and I think it makes a lot of sense doing it like this. N equals 3, the third quantum level. Any guesses how many orbitals? Follow the pattern. 1, 3,
6.
5.
Oh.
There's 5 sublevels on n equals 3, and these are d orbitals. D orbitals, which can hold a total of 10 electrons. And lastly, on the fourth level, n equals 4, I have 1, 2, 3, 4, 5, 6, 7. Guess what letter goes in those? F. There are 7 F orbitals holding a total of 14 electrons. Holding a total of 14 electrons. Then we have to fill these. We have to fill these. So, oops, maybe 2. This is how they fill. This is how they fill.
Oh, yes.
Oh, we're doing this again.
So, this is a little tedious, but I honestly think it helps. So, here's how they fill. So, if I was going to write this out, I'd fill 1s in the first level. Then it'd be like 2s, 2p. Then 3s, right? You guys remember doing this? 3p and then 3d. Yes? Fourth level, 4s, 4p, 4d, and then 4f. 5s, 5p, 5d, 5f. Then there's like an imaginary 5g.
What? A jug?
I know, it's kind of imaginary. If we discover more elements, all right? If we discover more elements, we're gonna need more orbitals.
What will it look like?
What it'll look like, we don't know yet. Haven't discovered it. 6s, 6p, 6d, 6f, 6g, 6h are my imaginary ones. I know. You can make anything up. 7s, 7p, 7d, 7f, 7g, 7h, 7i. That's it. So, I don't even have 7p's yet. All right? There's not even any 7p's, 7d's, or 7f's yet. But maybe in the future we're going to discover a lot more elements. All right, maybe we wheel in an asteroid. Have you guys heard about the asteroid that's worth like $80 billion floating out there that NASA's going to land something on?
What's on it?
Gold, precious metals,
That's it.
like tons of stuff.
But didn't astronauts work like
Tons of stuff.
Well, I feel like the inflation rate.
So, these fill down and to the left. So, my 1s orbital, if I fill in that, my first one goes 1s1. That's my first electron in my s orbital. And my second one goes here, 1s2. These are locations of electrons. You guys remember this? Yes? After that, I have to fill my 2s. So, I've got 2s1, 2s2. After that, I fill 2p and then 3s. So I'm going to have 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2. Yes? After that, I fill 3p, then 4s. So I have 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, 4s1, 4s2. After my 4s's, what do I fill next? I go 3d, 4p, then 5s. D's always trail by 1. 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. Back up to my 4p1, 4p2, 4p3, 4p4. What'd you say?
I'm a little blind.
4p6. I know. 5s1, 5s2. So that is the orbitals that I have filled so far. After my 5s's, I fill 4d, 5p6s. So now I'm going to do my 41, 42, 43, 44, 45, 46, 47, 48, 49, 40, 10. Back up to my 5p's, 5p1, 5p2, 5p3, 5p4, 5p5, 5p6, and then my 6s1, 6s2. After the 6s, this is where people make their mistakes. If you look over here, what fills next after 6s? F's. 4f, 5d, 6p, 7s. So after my 6s2, I go down here to 4f1, 4f2, 4f3, 4f4, 4f5, 4f6, 4f7, 4f8, 4f9, 4f10, 4f11, 4f12, 4f13, 4f14. And then up to my 5Ds, 5D1, 5D2, 5D3, 5D4, 5D5, 5D6, 5D7, 5D8, 5D9, 5D10. So 6Ps, 6P1, 6P2, 6P3, 6P4, 6P5, 6P6, 7S1, 7S2.
I am ridiculously far
You
behind.
can't write this fast?
No.
It's fine.
I can type this quickly, cannot write this fast.
It's fine. I'm going to finish it off. After my 7S, I fill 5F, 6D, and 7P. So after 7S, I go down here, 5F1, 5F2, 5F3, 5F4, 5F5, 5F6, 5F7, 5F8, 5F9, 10, 11, 12, 13, 14, and then 61, 62. I love how they sound like you're saying it 6D, like 6D4, 65, 6D6. It's how my family talks. 67, 68, 69, 6010. And then 7P1, 7P2, 7P3, 7P4, 7P5, 7P6. So that is our game board of where electrons are going to go.
Can I see the one with the arrows?
Yes.
Yeah.
Ooh, I can't get that built up. So there's the arrows, and then here is the game board. This should set us up for success to continue tomorrow. Plus, that was a lot of writing, so your hands are probably hurting. What's that?
Can I see the upper?
Yes. So, once you have this is a good stopping point for today. Good stopping point for today. So then tomorrow, we'll do electron configurations, which you guys all know how to do, or you should know how to do.
You like write it out.
Want us